Welcome to the Sleepy Brain Facts channel. Tonight, you embark on a journey into the wonders of the cosmos. This vast expanse is so immense that our minds can hardly grasp its scale. Far beyond our solar system, the universe brims with activity. For billions of years, worlds have formed and vanished in a seemingly endless cosmic cycle. Astronomy offers you a glimpse into this miraculous realm, where stars collide with unimaginable force. Planets wander through the infinite darkness, while unseen forces warp the very fabric of reality. You will encounter ancient galaxies that challenge explanation, colossal black holes that seem to defy the laws of physics, and countless marvels still waiting to be unveiled. If you find joy in these tranquil explorations, consider liking, subscribing, or sharing your thoughts below. Your engagement helps guide others to this space, one sleepy soul at a time. But for now, take a slow, deep breath. Allow your body to relax and your mind to ease. Let's begin. Stars can explode with a brilliance that outshines entire galaxies. When a massive star reaches the end of its life, its core can no longer bear its own weight, and gravity takes over. The core collapses inward at astonishing speed, compressing matter into a state more compact than anything you can experience on Earth. In an instant, a star collapses, sending shock waves racing through its outer layers. An immense surge of energy bursts into space as light, heat, and ethereal particles that slip through nearly everything. For a brief moment, this dying star shines brighter than the combined light of billions of suns. The explosion tears the star apart, scattering enriched materials into the surrounding cosmos. This debris carries newly forged elements, destined to become part of other stars, planets, and perhaps even life forms that will one day gaze back at that long-faded flash. Sometimes, planets drift aimlessly through space, untethered to any star. These lonely worlds are believed to originate in planetary systems similar to our own. In the early stages of these systems, young planets jostle against each other as they orbit their central star. If their dance becomes chaotic enough, one may be flung outward with such force that it escapes entirely. Once released, it journeys through the dark expanse between stellar neighborhoods, illuminated only by the faint light of distant suns. Without the steady glow of a nearby star, its surface may freeze solid, creating a crust of eternal night. Deep within the cosmos, remnants of heat from ancient formations and the slow decay of radioactive elements keep the interiors of celestial bodies warm for billions of years. Imagine thick atmospheres or hidden oceans on these distant worlds, concealing the chemistry that unfolds in their secret warmth as they drift silently through the vastness of space. Black holes, in their extraordinary nature, can spin so rapidly that they warp the very fabric of space around them. When a massive star collapses to create one of these enigmatic remnants, it retains not just its mass, but also its rotation. If this rotation is swift enough, it transforms the region surrounding the black hole into a whirlpool of distorted space-time. Everything nearby, from swirling gas clouds to fleeting particles, feels this twisting influence. Space itself begins to rotate, drawing matter into a spiraling dance that no engine could replicate. Close to the black hole lies a realm where nothing can remain still in relation to the distant universe. Even light is compelled to swirl, ensnared by the rotating geometry. This intriguing region, known as the ergosphere, allows energy to be harnessed from the spin, fueling powerful jets and high-energy emissions. In this way, the rotation of an invisible compact object can profoundly affect its cosmic surroundings, shaping the growth and behavior of its host galaxy over eons. Isn't it fascinating to think about how these unseen forces sculpt the universe around us? Take a moment to reflect on the mysteries that lie within the cosmos, inviting you to explore further, or perhaps simply to rest in the wonder of it all. Beneath the ancient ice, certain moons conceal oceans that are deeper than any found on Earth. In our own solar system, several small bodies orbiting giant planets display cracked surfaces adorned with ridges and streaks. These patterns suggest that something is moving beneath the ice. Measurements of their magnetic and gravitational fields indicate vast reservoirs of liquid water hidden beneath thick layers of ice, sometimes tens of kilometers deep. In these dark oceans, sunlight is absent, which means familiar forms of life cannot thrive, as they do on our planet. However, energy can originate from another source. As the moon orbits its parent planet, the shifting gravitational forces flex its interior, generating heat through a constant process of stretching and squeezing. This warmth prevents the water from freezing solid, even at great distances from the sun. On the rocky seafloor, hot vents may release mineral-rich fluids into the surrounding water, creating environments where complex chemistry can flourish. These hidden oceans serve as a reminder that habitable conditions might be more common than we think, even in seemingly cold and lifeless places. Galaxies can race toward one another at astonishing speeds. Gravity exerts its influence not just on nearby objects. On a larger scale, entire clusters and superclusters of galaxies move in response to each other's gravitational pull. This grand dance of cosmic bodies invites us to consider the mysteries that lie beyond our familiar horizons. As time passes, you witness an intriguing cosmic ballet, where two massive star systems embark on an inevitable collision course. Although their stars are so widely spaced that direct collisions are rare, their gravitational pull begins to distort the very shape of each galaxy. You can imagine great streams of stars and gas being drawn out into magnificent arcs and tails, stretching for hundreds of thousands of light years. When the clouds of gas from these galaxies encounter each other, they compress, igniting bursts of new star formation that dramatically alter the appearance of both systems. After a complex gravitational dance lasting hundreds of millions of years, these two galaxies can merge, transforming separate swirling islands of stars into a single, larger cosmic structure. This new formation often appears more rounded, resembling a grand cosmic city. Some stars cool so significantly that they begin to take on characteristics akin to giant planets. Not every object that forms from collapsing gas reaches the necessary temperature in its core to produce the nuclear reactions that power ordinary suns. Some fall short of this threshold, settling into a twilight state. They may start off relatively warm and bright, but over billions of years, they gradually release their heat into space, fading and cooling into the vastness of the cosmos. Take a moment to reflect on this extraordinary journey of stars and galaxies, and consider the beauty of transformation in the universe. Would you like to continue exploring this cosmic story, or perhaps take a moment to rest? As temperatures decline, the visible light from these celestial bodies diminishes, shifting into the infrared spectrum. Their atmospheres may contain clouds of metal-rich grains, droplets, and exotic molecules that cannot endure in the intense heat of true stars. At certain stages, the spectra and colors of these objects closely resemble those of massive gas giants. However, they do not fit the definition of planets. They formed independently from collapsing clouds, rather than orbiting a larger star. This places them in a unique category, illustrating that nature's creations often defy simple classifications. Comets, for instance, carry organic molecules that predate the existence of our sun. These icy travelers are believed to be remnants from the extensive gas and dust cloud that collapsed to form our solar system. Within that primordial cloud, tiny solid grains provided surfaces for atoms to bond and react under frigid conditions. Over time, simple substances like carbon monoxide and methane evolved into more complex compounds comprising chains of carbon, hydrogen, oxygen, and nitrogen. When clumps of ice and dust coalesced into comet nuclei, they preserved this ancient chemistry, a testament to the intricate processes that shape our universe. Take a moment to reflect on this fascinating interplay of elements and the mysteries that lie beyond our immediate understanding. Would you like to explore more about these cosmic wonders? As a comet approaches a star, its icy surface begins to warm, releasing gas and dust that create a glowing coma and a long tail. By analyzing the light emitted from these outflows, scientists discover a variety of organic materials, some of which resemble the fundamental building blocks of life. This suggests that the essential ingredients for biology can form in the depths of space, long before a planet takes shape from the swirling cosmic material. Nebulae can shine brilliantly when newly formed stars bathe them in intense radiation. In certain areas, clouds of hydrogen and other gases become dense enough to give rise to a new generation of stars. When the most massive of these young stars ignite, they emit powerful bursts of ultraviolet light. This radiation penetrates the surrounding clouds, stripping electrons from hydrogen atoms and creating large volumes of ionized gas. Later, as electrons recombine with protons, they release photons at specific wavelengths, resulting in vibrant colors that are visible through telescopes. These luminous regions can stretch across vast distances, their intricate shapes shaped by the interplay of gas density, stellar winds, and gravitational forces. Dark lanes of dust weave through the glowing material, casting striking silhouettes against the radiant backdrop. Isn't it fascinating to think about the beauty and complexity of these cosmic phenomena? You are invited to explore these wonders further, or simply take a moment to appreciate the vastness of our universe. As time passes, the combined effects of radiation and stellar outflows gradually erode the original cloud, creating bubbles and cavities, and eventually dispersing much of the gas into the vastness of space. Imagine extreme gravitational forces stretching planets into elongated, egg-like shapes. This fascinating distortion occurs when a planet orbits very close to a massive companion, causing a significant difference in gravitational pull between its near and far sides. This disparity creates tides not just in any oceans, but also within the rock itself. Over extended periods, these tidal forces can reshape a planet's overall form, pulling material toward the line that connects it to the object it orbits. Rather than maintaining a nearly spherical shape, such a planet may exhibit a noticeable bulge, its longest dimension directed toward its star. The continuous flexing of its interior generates heat, which alters its geology and can spark intense volcanic or tectonic activity. If the planet has an atmosphere, it may respond to this unique shape with powerful winds and intricate circulation patterns. Observing these distorted worlds offers astronomers a unique opportunity to study gravity's impact on solid matter in conditions that cannot be replicated here on Earth. Isn't it fascinating to consider how these distant planets reveal the mysteries of our universe? As you reflect on this, take a moment to appreciate the wonders of celestial mechanics and the stories they tell. If you're ready to explore more, or perhaps take a moment to pause, the choice is yours. Pulsars send out precisely timed beams of radiation that sweep across the sky, much like cosmic lighthouses. These fascinating objects are the quickly spinning remnants of massive stars that have ended their lives in explosive events. What remains is a remarkably compact core, about the size of a city, yet holding more mass than our sun. This core spins at breathtaking speeds, sometimes rotating numerous times each second and generating a powerful magnetic field. Charged particles trapped near the magnetic poles of the pulsar are accelerated to incredible energies, emitting focused beams of radio waves or even higher energy radiation. As the pulsar rotates, these beams sweep through space. If one of these beams crosses our path, we detect a pulse of emission. The intervals between these pulses can be astonishingly stable, rivaling the precision of atomic clocks. Astronomers harness these regular signals to test theories of gravity, investigate the distribution of matter in our galaxy, and even explore the subtle ripples in space-time created by distant pairs of orbiting remnants. In addition to pulsars, gas giant planets can generate storms larger than Earth that stubbornly persist. Within the immense atmospheres of these colossal worlds, towering layers of gas swirl and churn, driven by intense internal heat and rapid rotation. The cosmos is alive with wonders, inviting us to explore deeper into its mysteries. Would you like to continue this journey, or perhaps take a moment to reflect on the vastness surrounding us? Imagine a world where clouds are composed of substances that seem otherworldly to us: ammonia, methane, and even intricate crystals that form under immense pressure. These layers of gas glide past each other at varying speeds, creating zones of sheer turbulence. In these areas, chaos transforms into organized systems, leading to colossal atmospheric storms. Some of these rotating systems gain momentum over time, drawing energy from the planet's core. Without a solid surface to disrupt their flow, they can last for centuries. Their colors, shapes, and behaviors subtly shift, influenced by the surrounding atmospheric bands that either nourish or deplete them. Each storm evolves into a unique environment, complete with lightning, temperature variations, and towering cloud tops that rise dramatically above the lower atmosphere. These long-lived tempests reveal just how different weather can be on worlds where the laws of motion and heat operate on scales far beyond our own planet. In the vastness of space, entire galaxies can emerge with so few stars that they seem almost desolate. Astronomers have identified faint systems where only a smattering of stars glimmers against the profound darkness of the cosmos. These ethereal galaxies may have originated as ordinary clouds of gas, yet various cosmic forces can inhibit their ability to form new stars. As you reflect on these phenomena, consider the mysteries that lie beyond our understanding. Would you like to explore more about the wonders of the universe, or perhaps take a moment to pause and absorb what you've just learned? Interactions with larger cosmic neighbors can strip away the essential material needed for the birth of new stars, leaving only sparse remnants behind. In some instances, early generations of stars may have expelled much of the available gas through powerful winds, hindering subsequent formations. What remains is a structure primarily composed of dark matter, anchoring a delicate scattering of stars. Through careful observation and analysis, researchers can trace how these sparse systems adhere to the gravitational laws that govern more abundant galaxies. Their faintness unveils the hidden architecture of cosmic evolution, illustrating how environments, collisions, and ancient events can influence a galaxy's fate long before its stars become abundant. Even the dimmest of these stellar gatherings holds the history of forces that have acted over billions of years. A stellar remnant can shrink to the size of Earth while becoming remarkably dense. When certain stars exhaust their nuclear fuel, their outer layers drift away into space, leaving behind a compact core that no longer produces fusion. Without the outward force of nuclear reactions, gravity compresses the remaining material into a volume comparable to that of our own planet. As you reflect on this cosmic dance, consider the intricate stories held within these faint remnants. Each one carries a legacy, whispering the secrets of the universe's evolution. If you wish, take a moment to let these thoughts settle, or continue to explore the wonders of the cosmos. Imagine a small sphere, its mass rivaling that of the sun. Within this extraordinary compactness, atoms arrange themselves in ways that defy ordinary conditions. Electrons, acting in unison, create a unique form of matter that sustains itself through quantum mechanics rather than thermal pressure. Over vast stretches of time, these remnants gradually cool, releasing their stored heat into the cosmos. Their faint glow and distinctive spectral signatures provide astronomers with valuable insights into the transition from active stars to the final states they ultimately reach. These celestial bodies reveal behaviors of matter under extreme conditions, offering knowledge that earthly laboratories cannot replicate. Occasionally, planetary systems evolve, giving rise to planets orbiting at seemingly impossible angles. As newborn systems form from swirling clouds of gas and dust, they begin with disk that seem orderly and flat. However, over time, gravitational forces from nearby stars, passing objects, or massive planets can distort or twist the orbits of smaller worlds. The nature of these interactions can vary greatly, ranging from gentle nudges to violent encounters, depending on the masses involved and the timing of these celestial events. As the geometry of the cosmos begins to shift, resonances can amplify misalignments, sending planets onto paths that rise high above or drop far below the plane where their neighbors travel. When you observe exoplanetary systems, you discover worlds orbiting their stars at dramatic angles, challenging what we once thought about how planets form. By studying these unusual configurations, you gain insights into the diversity of cosmic environments. This exploration reveals just how fragile the earliest stages of planetary development can be. Each tilted orbit holds clues about events long past, events that reshaped the system in ways we are only beginning to understand. Consider the metal-rich asteroids scattered throughout the solar system. They contain more precious materials than Earth's crust. These fragments are remnants of ancient bodies that once endured intense heating, melting, and differentiation. In some of these early worlds, heavy elements like iron and nickel sank to the center, forming dense metallic cores. Long ago, collisions shattered some of these differentiated objects, scattering pieces across space. Today, when you detect these fragments, you often find asteroids composed of nearly solid metal, buried beneath thin layers of dust or silicate rock. The story of our solar system unfolds through these remnants, inviting you to delve deeper into the mysteries of our cosmic neighborhood. You discover that the interiors of certain celestial bodies can harbor concentrations of valuable elements that far exceed anything found on the surface of our planet. By examining their spectra and densities, scientists gain insights not only into potential future resources, but also into the tumultuous history of planetary formation. These metal-rich remnants act as a direct window into the internal structure of primordial worlds, revealing the processes that shaped the earliest solid bodies, long before planets settled into stable orbits and oceans of molten rock cooled into crusts. You observe that massive stars burn through their fuel at an astonishing rate, leading to their demise in the blink of a cosmic eye. Although these colossal stars contain far more hydrogen and helium than ordinary suns, their consumption of these elements occurs at a breathtaking pace. Their cores ignite with fierce energy, emitting intense light and heat that radiate outward. This powerful radiation generates a force strong enough to counteract the inward pull of gravity. As the star's mass increases, the struggle between brilliance and gravity intensifies. In relatively short periods, the immense pressure compels the core to fuse heavier elements, ultimately steering the star toward its inevitable collapse. Isn't it fascinating to consider how these cosmic giants shape the universe around them? Take a moment to reflect on the awe-inspiring processes that govern their existence. You might find beauty in their fleeting lives, a reminder of the delicate balance between creation and destruction. Feel free to continue this exploration, or take a moment to rest and absorb these thoughts. Imagine a universe where colossal stars blaze through their brief existence, illuminating the cosmos in ways that are almost ephemeral. While smaller stars may shine for billions of years, these giants live fast and die spectacularly. When they reach their end, their deaths reshape the very fabric of space around them. The heavy elements forged deep within their cores are cast outward, enriching the environments where future generations of stars and planets will emerge. Some planets reflect so much starlight that they appear to shine like tiny suns. Their brilliance stems from highly reflective cloud layers or surfaces composed of materials that scatter incoming radiation with astonishing efficiency. These worlds often orbit close to their stars, drenched in intense light that saturates their atmospheres and landscapes with a continuous glow. The chemical makeup of their clouds or icy surfaces influences how light dances off them, creating a radiance that can rival much larger celestial bodies. Some of these dazzling worlds reach scorching temperatures, causing minerals to vaporize into fine particles. These shimmering layers amplify their glow, making them even more captivating. Astronomers, with their keen eyes, can detect the reflected light from these planets, even when the planets themselves remain hidden from view. This reveals intricate details about their atmospheres and orbits, deepening our understanding of these extraordinary realms. As you ponder the wonders of the universe, consider how each star's end gives birth to new beginnings, shaping the cosmos in unimaginable ways. You are invited to continue exploring this vast expanse, or to take a moment to reflect on the beauty of it all. Their radiant glow aids researchers in understanding how various temperatures, pressures, and chemical combinations affect a planet's capacity to reflect radiation. Certain areas of space are home to magnetic fields that are millions of times more powerful than what we experience on Earth. These intense fields arise near compact remnants, dense clusters, or regions where charged particles traverse concentrated gravitational landscapes. As material spirals inward toward a collapsed object, it generates electric currents that enhance the surrounding magnetism. This process creates an invisible structure that directs particles along narrow pathways, accelerating them to remarkable energies. These robust magnetic zones influence the behavior of gas, dust, and radiation, impacting everything from jet formation to the release of brilliant bursts of light. In some instances, these fields become so powerful that they distort atoms, reshaping them into unusual forms that wouldn't occur under familiar conditions. By examining the light emitted from these environments, astronomers can uncover how magnetic forces interact with matter under extreme pressures and temperatures that we cannot replicate on Earth. This research enriches our comprehension of the physics that governs some of the universe's most extreme regions. As you reflect on these discoveries, consider how they expand our understanding of the cosmos. Would you like to explore more about the mysteries of space, or perhaps take a moment to rest? Galaxy clusters possess a remarkable ability to bend and stretch the light from distant stars into beautiful, luminous arcs. The immense mass contained within these clusters generates gravitational fields powerful enough to alter the paths of photons as they journey through space. When light from far-off galaxies passes close to these clusters, space itself curves, redirecting the light into new trajectories. At times, when the alignment is just right, a distant galaxy can appear warped or magnified. This results in stunning arcs, rings, or even multiple images of the same galaxy. Such distortions not only captivate the eye, but also reveal the distribution of both visible and unseen matter within the cluster. By observing these intricate patterns, researchers can uncover hidden structures composed of material that emits no light of its own. The faint stretched shapes act as a natural cosmic lens, amplifying objects that are too distant for direct observation. Each distorted image offers valuable insights into the universe's expansion, the growth of cosmic structures, and the enigmatic components that weave together the fabric of the cosmic web. As stars near the end of their life cycle, they sometimes release gas in complex, intricate shapes, resembling sculptures crafted by skilled hands. As these stars deplete their fuel, their outer layers loosen and drift away. Gentle pulses of energy push shells of gas outward, while swifter winds follow closely behind, reshaping the earlier material. Isn't it fascinating how the universe continually reveals its secrets through these magnificent processes? You might find yourself wanting to explore more about these cosmic wonders. The structures that emerge can take on various forms, like rings, hourglass shapes, or delicate filaments that twist through space in intricate patterns. Their colors are born from different elements glowing in response to the fading heat of stars. As time passes, the central remnant cools and dims, while the expanding gas spreads into the surrounding environment. Each of these structures reflects the internal rhythms, rotation, and magnetic influences of stars during their final active phases. These stunning forms illustrate the dramatic transformations that occur when stars reach the end of their lives, contributing enriched material to the galaxy. Star-forming clouds can collapse under their own gravity, giving rise to entire families of new suns. Across the galaxy, immense clouds of gas and dust drift in relative darkness until some disturbance disrupts their tranquility. A passing shockwave, the pull of a nearby cluster, or the influence of an earlier generation of stars can create subtle ripples in density. When a region becomes dense enough, gravity begins to draw its material inward. As this collapse accelerates, the cloud fragments into multiple pockets, each growing hotter and denser at its core. Within these pockets, pressure rises until the material starts to glow with the gentle warmth of a forming protostar. And as you delve into the cosmos, you notice how gas envelops each radiant center, forming swirling disks that guide the flow of matter, setting the stage for worlds yet to be born. Over time, a cluster of young suns arises from the same collapsing structure. Some of these stars are grand, while others are modest, and many may find themselves orbiting in companionship. These celestial families share a common beginning, their early tales etched in their movements and compositions, long after the original cloud has dissipated. You observe how planetary orbits can transform into unusual elongated shapes following gravitational encounters. When planets coexist with massive neighbors, their paths around their star can be subtly altered by interactions that unfold over extensive periods. A A close encounter between two worlds might gently push one outward, stretching its orbit into an elongated ellipse rather than a near-perfect circle. Further gravitational tugs from other bodies can amplify this effect, turning a once stable trajectory into something far more dramatic. These elongated orbits bring planets close to their stars at certain points in their cycles, while during other phases they retreat into the frigid reaches of space. This variation has the potential to reshape climates, alter atmospheric chemistry, and influence geological processes in profound ways. As you reflect on this cosmic dance, you sense the intricate connections that bind these celestial bodies and the ever-changing tapestry of the universe. Would you like to continue exploring these wonders, or take a moment to pause and absorb the beauty of it all? Even the smallest encounters can build up over time, gradually altering orbits into patterns that surprise us. When we observe distant systems, we see worlds moving in ways that hint at long histories shaped by gravitational forces. Each unusual orbit reveals a tale of past interactions, hidden events, and the unseen forces that mold the evolution of entire planetary families. Consider the powerful jets emitted by black holes, which can propel particles across distances larger than the galaxies that host them. Near the centers of some galaxies, swirling disks of superheated material spiral toward a compact object with an overwhelming gravitational pull. This pull is so intense that nothing crossing its inner boundary can escape. As material approaches this critical point, magnetic forces and rapid rotation can redirect some of it along tightly focused axes. These channels become launch sites for streams of charged particles propelled to speeds nearly that of light. Once these jets are unleashed, they cut through surrounding gas and travel outward for immense distances. Some even extend far beyond the galaxy itself, carving narrow paths through the vastness of intergalactic space. Along their journey, they illuminate clouds, ignite shock fronts, and warm clusters of material that might otherwise remain cold. Isn't it fascinating how these cosmic events interconnect, revealing the intricate dance of the universe? You are invited to continue exploring these wonders, or take a moment to reflect on them. Imagine the hidden power that lies within seemingly small remnants, revealing how these objects can significantly influence vast environments. The jets act as guiding lights, mapping the flow of energy from areas where gravity reigns supreme. Some moons experience intense tidal heating, strong enough to melt rock deep beneath their surfaces. As these moons orbit their parent planets, they often trace slightly oval paths, bringing them closer at times, and then pulling them farther away. This variation in distance alters the gravitational pull, stretching and compressing the moons repeatedly. This constant flexing creates friction inside, warming layers of rock and ice that would otherwise stay frozen. Over time, this accumulated warmth can lead to the melting of pockets of material, forming reservoirs of liquid beneath the surface. In certain cases, the heat generates plumes that burst through cracks, propelling vapor and particles into space. In others, it fosters slow circulation within hidden subsurface oceans, concealed beneath thick layers of ice. These internal processes transform landscapes from within, creating environments ripe for complex chemical reactions to thrive. Even in the face of extreme cold on its surface, the heat generated by tides reveals a fascinating truth. The movement of a moon through gravitational fields can transform its interior in ways that sunlight alone cannot achieve. Imagine ancient starlight traveling across the cosmos for billions of years before it finally reaches Earth. When a distant star or galaxy emits light, this light embarks on a journey through the ever-expanding fabric of the universe. As it travels, it weaves through regions filled with clusters, filaments, and voids, which can stretch or alter its color. Some wavelengths may be absorbed by gas clouds, while others continue their path unhindered until they reach our telescopes. The universe's vastness and constant expansion mean that the distance these photons travel is monumental. By the time they arrive, the sources that emitted them may have changed drastically or even ceased to exist altogether. This light transforms into a record of how those celestial objects appeared eons ago, frozen in time and preserved within its wavelength and intensity. Scientists harness these ancient signals to piece together the early chapters of cosmic evolution, allowing us to glimpse structures as they once were when the universe was still young. Each photon carries a story from its birthplace, crafting a timeline of events that would otherwise remain hidden from our view. As you reflect on this cosmic journey, consider the profound connections between light and time and how they reveal the universe's mysteries. Would you like to explore more, or take a moment to ponder this wonder? Dust-filled nebula can veil fully formed stars behind thick shadows. In certain regions of space, clouds of fine particles accumulate so densely that they block visible light from passing through. These dark nebulae appear as silhouettes against brighter backgrounds, concealing whatever lies within. Although the dust obscures your view, infrared observations reveal that many of these areas contain stars already glowing with heat. The dust grains absorb and scatter visible wavelengths, yet longer wavelengths manage to slip through more easily, allowing astronomers to glimpse the hidden interiors. Inside these nebulae, newborn stars gather material from surrounding gas, forming disks that may eventually give rise to planets. Remarkably, the same dust that conceals them plays a crucial role in cooling the cloud and facilitating its collapse. As the stars grow stronger, their radiation disperses the fog around them, unveiling clusters that have spent millions of years hidden from sight. This intricate dance between darkness and hidden light makes these nebulas essential laboratories for understanding how stars evolve from infancy to visibility. However, the cosmos can be harsh. Violent stellar winds can strip atmospheres from vulnerable planets. When massive or highly active stars emit streams of charged particles at high speeds, these winds sweep outward, filling the surrounding space with energetic flows. This dynamic interplay shapes the very fabric of our universe, inviting you to ponder the mysteries that lie beyond. Imagine a planet orbiting closely to a powerful star. Here, its upper atmosphere endures a relentless barrage of particles. Over time, these particles collide with atmospheric atoms, heating them up and granting them enough energy to break free into the vastness of space. Planets that lack strong magnetic fields are particularly vulnerable, as they don't have the protective barrier needed to deflect or redirect the incoming stellar winds. As the atmosphere gradually thins, the planet's surface faces increased exposure to harmful radiation and extreme temperature fluctuations. In some instances, this erosion can transform a once hospitable world into a desolate landscape. By examining how stellar winds interact with planetary atmospheres, scientists can discern which worlds might remain stable and which ones are at risk of long-term deterioration. These findings are crucial in guiding the search for environments that could potentially support life. Consider the high-energy radiation emitted by massive stars. This energy can sculpt nearby clouds into magnificent towering pillars. When young giants ignite within dense regions of gas and dust, they unleash intense ultraviolet light that radiates outward in all directions. This radiation ionizes the surrounding material, creating pressure that drives shock fronts, reshaping the cloud itself. Less dense areas evaporate swiftly, while regions with slightly higher density manage to resist erosion, creating a dynamic and ever-changing cosmic landscape. As time passes, these resistant clumps transform into elongated structures. Stripped of their surrounding gas, they rise into tall columns and ridges, pointing back to the energetic sources that shaped them. Inside these protective pillars, gravity continues its work, allowing new stars to form, sheltered from the harsh radiation of their surroundings. Observations of these formations reveal vibrant environments where creation and destruction occur side by side. The pillars stand as monuments, showcasing the immense power of massive stars and the resilience of the material from which future generations of stars will emerge. In the vastness of space, magnetic fields twist and confine blazing streams of charged particles. Across galaxies, these particles navigate environments sculpted by invisible magnetic structures. These fields originate from the movement of conductive gas, the rotation of stars, and the dynamics of compact remnants. When particles encounter these fields, their paths bend, spiraling around the magnetic lines instead of traveling in straight lines. In areas with strong magnetic fields, particles can become trapped and guided along narrow channels, forming streams that glow across multiple wavelengths. These confined flows may manifest as jets, arcs, or loops, tracing the intricate details of cosmic activity. As you explore the shapes and intensities of cosmic structures, you begin to understand how astronomers deduce the strength and orientation of the magnetic fields beneath them. The behavior of trapped particles offers a glimpse into how these magnetic forces influence energy distribution, star formation, and the evolution of vast cosmic structures. These interactions shed light on processes that are challenging to replicate within the confines of earthly laboratories. Consider the chaos of planetary collisions. In a single catastrophic moment, entire worlds can be reshaped. During the tumultuous early stages of a system's formation, numerous solid bodies travel along intersecting paths. When two substantial objects collide at high speed, the impact can lead to dramatic alterations in their structures. Mountains may melt, oceans could vaporize, and crusts might shatter. Some collisions result in the merging of bodies into a single, larger world, while others tear them apart, scattering fragments across the system. These fragments have the potential to reassemble into moons, rings, or smaller companion bodies. The heat generated by such impacts can create global magma oceans, completely resetting a planet's surface. Evidence of these ancient collisions persists in the form of cratered landscapes, unusual rotations, and unexpected compositions. As you reflect on these cosmic events, you can appreciate the profound forces at play in the universe. As you explore the cosmos, you discover how researchers study scars on planets to piece together their tumultuous histories. Each impact leaves a mark, revealing that even the most stable-looking worlds have been shaped by intense, transformative events. Consider the rings that encircle distant planets. These magnificent structures can stretch farther than the distance between Earth and the Moon. They form when material gets caught in orbit around a planet, rather than coalescing into a single moon. Dust, ice, and fragments of rock swirl in countless individual paths, each one responding to the pull of gravity and minor collisions with its neighbors. The brightness and texture of a ring system depend on the size and composition of its particles. Some rings sparkle gently, made up of fine, icy grains that scatter starlight beautifully. Others, composed of darker fragments, absorb more light, appearing faint even as they stretch across vast distances. In younger systems, collisions between emerging moons can create fresh debris that spreads into sweeping arcs. Over time, gravitational interactions shape the rings into narrow bands, gaps, and waves, creating patterns that shift gradually as the orbits evolve. When you gaze at the rings of distant worlds, you see more than just stunning structures. You witness the intricate dance of celestial bodies and the stories they tell. Take a moment to reflect on these wonders. What stories do you think the stars hold? You witness the remnants of ancient impacts, the dance of migrating moons, and the subtle forces that shape entire planetary systems. These expansive rings reveal the dynamic and varied nature of worlds, even those distant from the warmth of their stars. Some stars orbit so closely that they share outer layers of gas. In these remarkable binary systems, two stars exist in proximity, their gravitational fields overlapping in a cosmic embrace. As they evolve, one star may swell into a giant, its outer layers spilling over toward its companion. This flowing material creates a bridge between the two bodies, forming a swirling region where gas circulates, influenced by the pull of both stars. This exchange can significantly alter their destinies. The star receiving the material gains mass, growing hotter and brighter, while the star losing its layers becomes stripped, revealing deeper layers that would typically remain concealed. The shared atmosphere can generate intricate patterns of heat and motion, leading to eruptions, flares, or pulses of radiation that vary at regular intervals. Observing these systems provides astronomers with a unique perspective on stellar evolution. The stars influence each other in ways solitary stars never experience, showcasing how companionship in the cosmos can yield outcomes far more dramatic than either star could achieve on its own. Dense globular clusters are remarkable formations, packing hundreds of thousands of stars into tight spheres. These ancient collections orbit the fringes of galaxies, shining like beacons of stellar history. Each cluster consists of stars that formed around the same time, making them some of the oldest surviving structures in the universe. In these densely packed environments, stars are much closer together than in typical regions of a galaxy. This proximity leads to frequent gravitational encounters among the stars. Such interactions can fling some stars outward, pull others inward, and alter their orbits, creating an ever-changing internal landscape. Among the stars in these clusters, you might notice some that are unusually blue and bright. These unique stars likely formed from mergers or mass transfer events triggered by those close encounters. Despite the constant motion within, the clusters maintain their tight formations because their combined mass keeps the stars bound together. Studying these clusters provides valuable insights into how early star formation occurred and how nature preserves these ancient spheres over cosmic time. The interstellar medium can carry shock waves from ancient supernova explosions. When a star explodes, it releases a powerful wave of energy and material that sweeps through the surrounding space, leaving a mark on the cosmos. As you reflect on the beauty and complexity of these stellar formations, consider the stories they hold and the mysteries they continue to reveal. Feel free to take a moment to ponder or explore further. The interstellar medium may seem sparse, yet it holds gas, dust, and charged particles that can be influenced by shock waves. As these waves travel through space, they heat the materials they meet, sometimes igniting new chemical reactions or causing atoms to emit vibrant colors. These waves can expand for millions of years, sculpting nearby clouds and playing a crucial role in the formation of new stars. The effects of these waves stretch across vast distances, leaving behind intricate shells, bubbles, and filaments that trace the remnants of ancient explosions. By studying these patterns, astronomers can estimate when the original supernovae occurred and the energy they unleashed. Each shockwave acts as a messenger from a long-gone star, conveying information through the subtle changes it leaves on the interstellar medium. Some planets orbit their stars at such incredible speeds that their years last only a few Earth days. These worlds travel in tight orbits, where gravity guides them along dizzying paths. With each rapid revolution, they endure extreme radiation and dramatic shifts in temperature, facing challenges unlike any found in our solar system. On the side facing the star, temperatures can soar to levels that melt rock or vaporize minerals. Meanwhile, the far side experiences a dramatic drop in temperature unless strong winds manage to distribute heat effectively. The rapid pace of each orbit creates distinctive atmospheric patterns as currents struggle to keep up with the swift cycle of day and night. Some planets are locked in such a way that one side always faces the star, heightening the contrast between intense light and profound darkness. By exploring these extreme environments, scientists gain insight into how planets react to conditions far removed from those on Earth. The brief lifespans and scorching climates of these worlds broaden our understanding of the possibilities for other celestial bodies. Spiral galaxies, too, can develop new arms as they interact with neighboring systems. The elegant spirals that characterize these galaxies may seem stable, yet their forms are shaped by the gravitational forces exerted by surrounding objects. When another galaxy passes nearby without even making direct contact, their gravitational pull can disrupt the arrangement of stars and gas within the spiral. Waves of density ripple through the disk, compressing material into arcs that gradually evolve into new arms. These arms are not fixed structures. Rather, they represent moments where stars cluster together before eventually drifting apart. As gas within the arms of a galaxy becomes denser, it fosters the birth of vibrant young stars, enhancing the galaxy's spiral form. Over millions of years, these repeated interactions can reshape the galaxy's structure entirely. Sometimes, new arms emerge while older ones fade or twist into distorted loops. Observing these transformations offers insights into how galaxies evolve through encounters and how the cosmic environment influences their long-term development. Massive star clusters illuminate the surrounding gas with their intense ultraviolet radiation. Clusters filled with many hot young stars emit significant amounts of high-energy light that radiates outward in all directions. When this radiation encounters nearby clouds of hydrogen-rich gas, it strips electrons from the atoms, heating the cloud in the process. This interaction causes the gas to glow in a distinctive array of colors, revealing its composition and temperature. The region surrounding these clusters transforms into a brilliant nebula featuring tendrils and shapes sculpted by cosmic forces. Winds from the stars push the gas outward, while the radiation carves out pillars, ridges, and cavities. As the cluster evolves, the brightest stars burn out rapidly, leaving behind a dynamic landscape of light and shadow. You may find yourself reflecting on the beauty and complexity of these cosmic processes. Perhaps you feel a sense of wonder about the universe's ever-changing nature. Take a moment to appreciate this magnificent dance of creation and transformation. The illuminated regions of the universe help you understand how star formation unfolds within clusters and how young stellar communities impact their surroundings. The brilliance of these areas illustrates the influence that a single cluster can have on the cosmic neighborhood around it. Imagine rogue stars racing through intergalactic space at incredible speeds. These solitary travelers are believed to have been expelled from their home galaxies due to gravitational encounters that propelled them forward with astonishing momentum. Some may have ventured too close to a supermassive black hole, while others were ejected during intricate interactions among multiple massive stars. Once released, they speed through the vastness of space without a galaxy to call their own. Their paths lead them into regions where starlight is dim and matter is scarce, making them challenging to detect. Yet their velocities and trajectories provide vital clues about the tumultuous events that launched them. By observing their motion, you can trace back to the violent moments that set them free. Even in isolation, these stars carry the chemical signatures of their origins, offering insights into the environments from which they emerged. Their journeys serve as a poignant reminder that even stars can undergo dramatic displacements, wandering across the immense emptiness that exists between galaxies. Imagine a vast cosmic scene where planetary systems come to life, adorned with multiple asteroid belts that resemble celestial rings. As these systems form, remnants from the birth of planets linger in stable orbits around their stars. These belts are composed of countless rocky fragments, ranging from tiny grains to substantial bodies, each telling a part of the story of the system's evolution. Over time, the gravitational pull of nearby planets shapes these belts, creating distinct regions rather than a continuous expanse of debris. Gaps emerge between the belts, where resonances disrupt orbits, leaving clear paths that remain unoccupied. Each belt serves as a testament to the system's history, revealing how collisions, migrations, and gravitational forces have sculpted the debris. The existence of multiple belts hints at a complex past, marked by interactions that influence the arrangement of planets in their current positions. As astronomers examine these structures in distant systems, they draw parallels to familiar features like our own asteroid belt and the Kuiper belt. These comparisons enrich our understanding of planetary evolution and how patterns of debris reflect a system's early history. Meanwhile, quasars, those magnificent beacons of light, shine with the brilliance of trillions of stars combined. These extraordinary objects reside in the hearts of young, active galaxies, where immense amounts of gas spiral towards supermassive black holes, creating a spectacle of cosmic energy. Take a moment to ponder the wonders of our universe and how each element contributes to the grand tapestry of existence. Whether you choose to explore deeper or simply reflect on these marvels, the cosmos invites you to continue your journey of discovery. As material spirals inward, it transforms into a disk that heats up to extreme temperatures due to friction and compression. This disk emits energy across the electromagnetic spectrum, producing a brilliant luminosity that can outshine an entire galaxy. Surrounding clouds absorb and re-emit this radiation, generating strong spectral features that reveal the physical conditions near the core. Despite their dazzling light, the central regions that power the quasar remain surprisingly compact. The energy output fluctuates based on the rate at which matter falls inward, a process that can change over time. When we observe quasars at varying distances, we see that these energetic objects were much more common in the early universe. This period marked a time when galaxies were rapidly evolving and feeding their central black holes. Their immense energy allows them to be visible across vast cosmic distances. Astrobiologists are engaged in the study of planetary atmospheres to search for chemical signs of life. To determine if a distant world could support living systems, researchers meticulously analyze the gases surrounding it. As starlight filters through a planet's atmosphere, During its orbit, the light carries subtle imprints from the molecules it encounters. This careful examination helps uncover the potential for life beyond our own planet. Sensitive instruments have the ability to break down light into its various colors, revealing substances that may indicate biological activity. Gases like oxygen and methane are particularly intriguing, as they tend to disappear quickly unless something replenishes them. On Earth, living organisms play a crucial role in maintaining these gases through their constant interaction with the environment. Astrobiologists work diligently, blending atmospheric models, laboratory experiments, and observations across different wavelengths. They aim to determine whether unusual chemical combinations could arise from natural processes alone, or if they require something more dynamic. Their research is approached with caution, as planets can produce unexpected chemistry even in the absence of life. Nevertheless, each atmosphere they analyze contributes to a growing library of possibilities. This expanding knowledge is essential for refining the search for planets that might support stable climates, liquid water, and enduring cycles conducive to biology, whether familiar or entirely alien. Some moons undergo constant transformation due to cryovolcanic eruptions, harboring warm interiors that keep certain materials melted beneath their icy surfaces. Instead of molten rock, these hidden reservoirs hold mixtures of water, ammonia, nitrogen, and other volatile substances that remain liquid at low temperatures. As you contemplate this fascinating journey, consider the wonders that lie beyond our world and the potential for life in the cosmos. Pressure builds beneath the surface, where oceans and chambers shift and churn, as pathways open through cracks or weak points in the ice. Pressurized material escapes in plumes, rising into space or cascading across the landscape. Over time, these eruptions sculpt smooth plains, ridges, and textured formations, replacing older terrain. This process of resurfacing can conceal impact craters and erase geological features that would otherwise tell a long history. By observing these ever-changing landscapes, scientists gain insights into how internal heat, tidal forces, and complex chemistry sustain activity in worlds far from their stars. The existence of liquid environments beneath the surface raises profound questions about what life might thrive in these energy-rich habitats. Gravitational lensing offers a glimpse into the cosmos, magnifying galaxies that would otherwise remain hidden. As light journeys across the universe, it traverses regions shaped by the distribution of mass. When a massive object lies in the line of sight between the observer and a distant galaxy, the curvature of space around that mass alters the path of the light. This effect can stretch, brighten, or multiply the appearance of the background galaxy, revealing the wonders of the universe in ways that captivate our imagination. As you observe the cosmos, instead of just a faint smudge, you might notice arcs or rings that illustrate how light bends through space. This magnification offers astronomers a unique opportunity to explore structures from the universe's infancy. It reveals insights into star formation, dust content, and the early assembly of galaxies. By studying the distortion of light, researchers can map the mass of the lensing object, including elusive dark matter that remains invisible to the naked eye. Each lensing event acts as a natural telescope, crafted by gravity itself, providing a glimpse into regions far too distant for direct observation. In stellar nurseries where stars are born, young stars flicker unpredictably as clouds of dust drift across your line of sight. These areas are rich with gas and dust, creating an environment where stars begin their journey. Young stars often have swirling disks of leftover material, which will eventually give rise to planets, moons, and smaller celestial bodies. Clumps within these disks can occasionally obscure or dim the light from the star, leading to fluctuations that may seem erratic. The dust distribution shifts continuously due to winds, magnetic fields, and gravitational forces, resulting in some stars dimming slowly while others brighten quickly or exhibit chaotic changes. As you contemplate this cosmic dance, take a moment to reflect on the beauty and complexity of the universe. You are invited to explore further or simply pause and absorb the wonder around you. These patterns provide insights into the structure and behavior of the disks around them. As scientists study the flickering, they can identify rings, gaps, warps, and areas where material gathers. The variations also indicate potential planets forming within these disks, as their gravitational influence shapes the surrounding dust. These early changes highlight the dynamic environment where solar systems begin their journey toward maturity. Some galaxies expand by steadily consuming smaller companions. They do not always evolve in isolation. In crowded cosmic neighborhoods, large systems frequently encounter smaller ones. Gravity gently pulls them together, causing the smaller galaxy to lose stars and gas as it spirals inward. Streams of material trail behind, leaving luminous paths that mark the cosmic meal. These mergers can ignite bursts of star formation when gas clouds collide and compress. Over time, the larger galaxy absorbs the stars of its companion, enriching its halo and inner regions. The chemical signatures of these absorbed stars differ slightly from those already present, allowing astronomers to trace the history of past mergers. This gradual growth process significantly shapes the structure of galaxies, helping to explain why many exhibit complex layers, extended halos, and subtle variations in their stellar populations. As you explore the cosmos, each consumed companion merges into a larger whole, its essence lingering only in faint traces. The atmospheres of certain exoplanets shimmer softly, warmed by the embrace of starlight. When a planet orbits closely to its star, it experiences intense radiation that elevates its atmosphere to temperatures far beyond what you find on Earth. In this heated state, excited molecules and atoms release energy, creating a delicate glow detectable in both infrared and visible light. This gentle emission unveils details about the gases present, their temperatures, and the atmospheric dynamics at play. Sometimes, this glow shifts across the planet's surface as winds carry warmth from the sunlit side to the dark. In some worlds, chemical reactions ignited by ultraviolet light produce compounds that enhance their brightness. By monitoring these subtle emissions throughout different orbital phases, scientists piece together weather patterns, thermal gradients, and atmospheric circulation on planets that appear as mere points of light. The soft glow enveloping these distant worlds serves as a glimpse into environments sculpted by powerful stellar energy. Meanwhile, planetary nebulae signal the final breaths of medium-sized stars, reminding you of the intricate dance of life and death in the universe. As you reflect on these cosmic wonders, consider the stories they tell of transformation and existence. As stars similar in mass to our Sun approach the end of their life cycles, they begin to shed their outer layers. This process unfolds through gentle winds and gradual pulsations. The layers drift outward, illuminated by the hot core that remains, casting a brilliant ultraviolet light. This light causes the gas to glow in vibrant colors, revealing the composition and density of the expanding shell. Depending on the star's rotation, magnetic fields, or interactions with nearby companions, these shapes can manifest as rings, ovals, or intricate patterns. Over time, the nebula continues to expand, slowly thinning until it eventually fades into the vastness of interstellar space. Meanwhile, the exposed core cools, transforming into a compact remnant that will emit a faint glow for billions of years. Planetary nebula offer us a glimpse into the process by which stars recycle material back into the galaxy. They enrich future generations of stars and planets with heavier elements, marking a transition from the vibrant life of a star to a tranquil final stage. In the grander scheme, supermassive black holes play a crucial role in regulating star formation across entire galaxies. At the centers of many galaxies, these colossal black holes draw in material, forming swirling disks. When this inflow becomes intense, the area surrounding the core releases immense energy, which radiates outward through jets, winds, and radiation. As you reflect on these cosmic processes, consider the profound connections between life cycles in the universe and the material that shapes our existence. Each moment in this celestial dance invites you to explore further, to understand the mysteries that lie beyond our world. Outflows from the central black hole heat the surrounding gas, pushing it away from the heart of the galaxy. When this gas becomes too warm or sparse, it loses the ability to collapse and form new stars. This dynamic shows how the central black hole governs the growth rate of the entire galaxy. In galaxies with active centers, star formation in the inner regions often diminishes. Conversely, those with quieter centers can maintain a steady rate of star creation. This intricate balance between feeding the black hole and allowing for new stellar populations is crucial for understanding the diverse appearances, behaviors, and long-term fates of galaxies. Some stars follow orbits that tilt dramatically above the Milky Way's disk. While most stars remain within the thin disk, a notable number travel along paths that rise high or dip low. These tilted orbits may result from ancient gravitational interactions, mergers with smaller galaxies, or disturbances caused by massive objects. As these stars navigate their inclined paths, they provide a three-dimensional perspective of the galaxy's structure. Their movements assist astronomers in mapping the distribution of mass, including elusive dark matter that remains hidden from direct observation. Some of the stars you see in the night sky may be remnants of ancient dwarf galaxies, carrying unique chemical signatures that set them apart from the stars we typically observe. Their unusual orbits tell a story about the dynamic history of the Milky Way, revealing how past events have shaped a structure that now seems calm and stable. When a massive star meets its end in a dramatic explosion known as a supernova, it sends shock waves rippling through the cosmos. These waves can ignite new waves of star formation. As the expanding blast collides with surrounding molecular clouds, it compresses the gas and dust within them, increasing the density in regions that were once too diffuse to collapse under their own weight. When this compression reaches a critical point, gravity takes over and the cloud begins to contract. In the aftermath of this explosive event, new stars emerge, transforming destruction into creation. This cycle breathes new life into various regions of the galaxy and facilitates the recycling of material through generations of stars. By studying these sites of triggered star formation, scientists can trace the sequence of events that connects the death of one star to the birth of many others. The timing, shapes, and locations of these new clusters offer valuable insights into how the shock wave traveled and the extent of its influence. These cosmic interactions highlight the interconnectedness of stellar processes, where the end of one life serves as the catalyst for countless new beginnings. Imagine a pair of binary stars so closely entwined that one draws material from the surface of the other. In these extraordinary systems, the stars orbit each other at such close distances that their gravitational fields intertwine in a delicate yet powerful balance. As one star evolves and expands, its outer layers can swell beyond the reach of its own gravity. When this occurs, gas from these outer layers drifts toward its companion, creating a flowing bridge of material suspended in space. The receiving star often gathers this falling gas into a spiraling disk, which grows hotter and denser with each new influx. This transfer of material can dramatically transform both stars involved. The donor star becomes stripped, revealing deeper layers that would typically remain hidden, while the companion star increases in mass and brightness. You might witness sudden bursts of brightness when the accreted gas heats up rapidly or undergoes explosive reactions. These complex interactions provide scientists with insights into how close companionship can dramatically reshape the lives of stars, experiences that solitary stars never encounter. As you contemplate this cosmic dance, consider the tiny grains of dust that can contain crystalline structures formed in dying stars. These minute particles journey through interstellar space, carrying with them the signatures of the environments where they originated. Isn't it fascinating how interconnected the universe is, even at such vast distances? As you explore the vast cosmos, consider the outer layers of aging stars. Here, gas cools and condenses, transforming into solid grains as the star releases its material into the surrounding space. In the right conditions, atoms align into orderly patterns, forming crystals that possess unique chemical signatures. When supernova blasts and powerful stellar winds occur, these grains are scattered across the galaxy, mingling into clouds that will eventually give rise to new stars and planets. Scientists, through careful analysis of the light reflected or absorbed by this cosmic dust, uncover subtle features that reveal the presence of these crystalline structures. Some of these grains are even older than our solar system, serving as ancient relics of stars that have long since faded away. Their composition provides insight into the cycle of material that flows from one generation of stars to the next, illustrating how the universe endlessly recycles the very building blocks of planets and possibly the ingredients for life itself. In stellar nurseries, intricate networks of filaments emerge, filled with newborn suns. Within these dense clouds of gas and dust, gravity pulls material together, forming long strands that weave through the darkness like luminous threads. These filaments serve as natural highways, guiding matter toward regions where new stars are beginning to ignite. As you reflect on this cosmic dance, consider how interconnected everything is, from the tiniest grains to the grandest stars. You are part of this incredible journey, woven into the fabric of the universe. If you wish, take a moment to pause and absorb this wonder, or continue your exploration into the mysteries of the cosmos. As gas gathers, knots form along the filaments, each one gradually becoming hotter and denser. Eventually, these knots collapse and ignite, giving birth to young stars surrounded by swirling disks of leftover material. The filaments themselves twist and bend, influenced by magnetic fields and turbulent motions, creating a dynamic tapestry of shapes that evolve slowly over time. Observations across various wavelengths reveal how material flows through these networks, with different temperatures highlighting distinct structures. These stellar nurseries offer a glimpse into the earliest stages of star development, illustrating how interconnected processes lead to the formation of entire clusters rather than isolated stars. Each glowing thread represents a pathway through which the galaxy continually renews itself. Some planets develop thick hydrogen atmospheres that overshadow their rocky cores. These massive envelopes form when a young planet grows quickly enough to capture light gases before the surrounding disk disperses. Hydrogen and helium stream toward the developing world, accumulating in amounts that far exceed the mass of the rocky material beneath. Over time, the atmosphere transforms into a vast layer, rising high above the core, seamlessly blending from dense lower regions into the thin outer edges. Within the vastness of space, temperatures and pressures inside certain envelopes can reach astonishing extremes. These conditions give rise to unique chemical processes that aren't typically found on smaller planets. Imagine winds racing through the atmosphere at incredible speeds, transporting heat from one area to another. This creates dynamic weather patterns that can envelop the entire planet. Although the rocky core remains hidden from our sight, the atmosphere itself tells a rich story about the planet's history and environment. It holds clues about the early formation stages, offering insights into how planets evolve and why some gather more gas than others. As you gaze into the cosmos, consider the chemical fingerprints left in starlight. When a planet transits in front of its star, some of that starlight filters through the planet's atmosphere before reaching us. Each atom or molecule has a unique way of absorbing specific colors of light, creating subtle yet distinct patterns in the spectrum. By examining these patterns with advanced instruments, scientists can deduce the presence of gases that may reveal information about a planet's climate, weather, or even geological activity. This technique opens up a world of possibilities, enabling researchers to study planets that are too faint or distant to be directly imaged. It allows for exploration of worlds that are not only smaller, but also cooler than we ever thought possible. As you reflect on this, you might find yourself curious about the mysteries waiting to be uncovered in the universe. Would you like to continue this journey of discovery? Or perhaps take a moment to rest and ponder. As you delve into the wonders of the universe, you discover that data gathered from various planets reveals fascinating trends in atmospheric chemistry. These trends reflect the unique histories and environmental conditions of each world. This cosmic fingerprinting allows you to examine distant planets using only the light that filters through their atmospheres. It stands as one of the most powerful methods for studying far-off atmospheres, eliminating the need for costly probes or missions. Scattered throughout the Milky Way are relics of ancient galaxies. Long ago, smaller galaxies drifted close enough to the Milky Way for its gravity to pull them in, and instead of remaining intact, many were gradually torn apart as they spiraled inward. Their stars stretched into elongated streams, wrapping around the galaxy like delicate trails of stardust. These remnants manifest as thin ribbons of light, tracing the orbits of the systems that have long since been consumed. Each of these streams carries a unique chemical signature, distinct from the stars born within the Milky Way itself. This allows astronomers like you to identify their origins. By mapping their paths, researchers can reconstruct the merger events that have shaped our galaxy over billions of years. Some of these relics still appear as faint clusters, holding together, while others have dispersed into the broader halo of stars. As you reflect on these cosmic tales, you might feel a sense of wonder about the vastness of space and the stories it holds. You are invited to continue exploring or to take a moment to rest and absorb the beauty of this knowledge. You find yourself immersed in a captivating narrative of the cosmos. Together, these celestial bodies create a historical record, preserved in the shimmering starlight. They reveal how the Milky Way has grown, gradually absorbing its smaller neighbors over eons. As you gaze into the depths of space, you notice some stars surrounded by dusty disks. These remnants are left over from the formation of planets. Within swirling clouds of gas and debris, planets take shape, but leftover material often remains in orbit around the star. You can imagine the collisions between smaller bodies, continually grinding fragments into fine dust that spreads throughout the system. This dust, in its quiet dance, absorbs starlight and re-emits it at longer wavelengths. This unique signature can be detected by specialized telescopes, revealing secrets of the universe. The structure of these disks varies, influenced by the presence of planets that carve gaps, shepherd rings, or scatter material into new configurations. As you observe the distribution and temperature of the dust, you uncover the architecture of the system. This knowledge helps you identify regions where planets might still be forming, hinting at the dynamic processes at play. Over time, radiation pressure and collisions gradually remove the material, yet some disks endure for hundreds of millions of years. These dusty rings serve as archives, preserving early planetary history and offering clues about the intricate processes that shape the worlds orbiting the central star. You might also notice intergalactic gas stretching in narrow filaments, connecting distant clusters, adding to the vast tapestry of the universe. Take a moment to reflect on this grand narrative and consider how these cosmic stories continue to unfold around us. In the vastness of the universe, you notice that matter is not evenly spread out. Instead, it gathers into immense structures, creating a cosmic web of clusters, nodes, and connecting strands. These filaments are made up of diffuse gas, enriched with elements that were forged in the hearts of earlier stars. Although they are incredibly faint, they stretch across vast distances, channeling material into the galaxies that are growing around them. As you explore further, you discover that these filaments play a crucial role in guiding the motion of galaxies and influencing the evolution of clusters. Gravity pulls matter along these strands, while interactions between gas and dark matter shape the development of large-scale structures. To study these filaments, scientists utilize sensitive instruments capable of detecting subtle signals from hot or ionized gas. The existence of these filaments not only confirms theoretical models of cosmic evolution, but also illustrates how the universe organizes itself on grand scales. Through these cosmic threads, galaxies receive the essential raw materials needed to form new stars and expand their stellar populations. You might find it fascinating that cosmic magnetic fields also come into play, influencing the motion of charged particles over enormous distances. These fields emerge from the movement of conductive plasma within stars, galaxies, and intergalactic gas. Once established, they create invisible pathways that guide the movement of electrons and ions. As you reflect on this intricate cosmic dance, consider how interconnected everything is. The universe has its own rhythm, and you are a part of it. If you wish to delve deeper into this cosmic journey, or take a moment to rest in contemplation, the choice is yours. You observe charged particles spiraling along magnetic lines. They travel vast distances, emitting radiation that signals their presence. The strength and orientation of these magnetic fields fluctuate, influencing the behavior of cosmic rays and shaping the structures of nebulae and jets. In areas where magnetic activity is complex, particles may become ensnared in loops or directed into narrow beams that extend far from their origins. As you delve deeper into these interactions, you begin to understand how they help astronomers trace the flow of energy in environments where gravity, pressure, and magnetic forces intertwine. The impact of magnetic fields illustrates how unseen forces play a crucial role in the universe's dynamics. Consider planets that orbit dead stars, which emit little more than a faint, ghostly light. When a star of moderate mass reaches the end of its life, it sheds its outer layers, leaving behind a compact remnant that gradually cools over time. These remnants emit only a dim glow. However, some still host planets that have endured the dramatic changes of their parent stars. Imagine these faintly lit worlds surrounded by a chill that makes them far colder than those orbiting ordinary stars. Any surviving planets likely experienced extreme heating during earlier phases, only to be followed by prolonged periods of deep freeze as their stellar remnant faded away. Imagine a universe where planets dance around their stars, some entwined in a close embrace, feeling the pull of strong tidal forces, while others drift serenely in the cold, distant reaches of space. As you delve into the study of these celestial systems, you uncover the remarkable resilience of planetary bodies, enduring extreme changes and adapting to the shifting conditions of their stars. Even when their stars fade and lose their brilliance, these planets continue to exist, a testament to their enduring nature. Consider the gas giants, where their atmospheres glow with a soft light in infrared wavelengths. Deep within these colossal worlds, heat rises from their cores, escaping through thick layers of gas. Much of this warmth is emitted as infrared light, a form of energy invisible to the naked eye, but detectable by specialized instruments. This gentle glow forms as atmospheric gases absorb energy, releasing it as radiation. This steady output provides insights into the temperatures, movements, and chemical compositions of these distant atmospheres. Winds carry heat across their surfaces, shaping patterns that evolve slowly over time. In some of these gas giants, powerful storms stir the atmosphere so intensely that warm regions from the depths rise, shining more brightly than their surroundings. As you observe this faint infrared light, you gain access to the hidden workings of planets that remain mere points of light in the vast sky. These glowing atmospheres reveal the intricate dance of energy as it moves through layers of swirling hydrogen and helium. This glimpse into their environments offers a perspective that dwarfs any weather system we know on Earth, inviting you to explore the mysteries of the cosmos. Would you like to continue this journey of discovery, or take a moment to reflect on the wonders of the universe? Tidal interactions have the power to reshape stellar envelopes into elongated forms. When two stars orbit closely, their mutual gravity exerts a strong pull on their outer layers. This pull isn't uniform. The side of each star facing its companion feels a stronger force than the side facing away. Over time, this uneven pressure stretches the outer regions of the stars along the line connecting them. As a result, the stars become slightly elongated rather than remaining perfectly round. This distortion evolves gradually as the stars continue their orbits, leading to subtle changes in brightness that reveal their stretching. In some systems, the effect can be so pronounced that it influences the star's rotation and the movement of energy within their interiors. The twisted shapes may also impact how stars shed material or exchange gas with their companions. These interactions illustrate how gravity can sculpt stars, much like it shapes planets and galaxies. They leave behind visible signatures that unveil the forces at play. In some galaxies, you may find enormous cavities where past explosions have cleared out vast regions of gas. Observations show these hollowed-out areas appearing strangely empty compared to their surroundings, inviting curiosity about the cosmic processes that created them. Imagine a vast expanse of space, where powerful cosmic events unfold, shaping the very fabric of galaxies. You might wonder how these magnificent cavities come into existence. They are created when immense energy releases gas outward, a phenomenon seen in exploding stars, energetic outflows from central black holes, or bursts of intense star formation. As these shock waves ripple through the galactic environment, they sweep away gas and dust, forming large visible bubbles that linger long after the initial event has passed. Each cavity tells a story, capturing the history of the forces that shaped it. Over time, these bubbles may stretch, fragment, or refill as new material drifts inward. By studying these features, you gain insight into how galaxies manage their gas supply and how energetic events influence the birth of new stars. Each cavity stands as a testament to a moment of dramatic change, reshaping its host galaxy from the inside out. In the cold reaches of space, interstellar clouds play a fascinating role. They can freeze molecules onto dust grains, creating icy layers. In the coldest regions, temperatures drop so low that gases behave in unexpected ways. Molecules drifting through these dark clouds may become trapped on the surfaces of dust particles. Once they attach, they form thin, icy coatings that accumulate layer by layer over time. These frozen layers often contain water, carbon dioxide, methane, and other compounds, all solidified in the frigid embrace of space. As you reflect on these cosmic processes, consider the intricate dance of creation and transformation that unfolds in the universe. Each moment, each cavity, contributes to the grand narrative of galaxies and their evolution. You are invited to continue exploring this captivating journey, or simply take a moment to rest in the wonder of it all. As cosmic rays and faint ultraviolet light filter through the clouds, they trigger slow chemical reactions within the ice. These reactions forge more complex molecules, enriching the cloud with materials that may later play a role in the creation of stars and planets. Eventually, when the cloud collapses, the heat from forming stars evaporates the ice, releasing its chemical treasures into the surrounding gas. These icy grains serve as tiny storage sites, preserving the earliest stages of chemical evolution in the galaxy. When massive stars collapse, they can give rise to stellar mass black holes. A star, many times larger than the Sun, spends its life fusing heavy elements in its core until the reactions can no longer support its weight. As the outward pressure fails, gravity pulls the core inward with tremendous force. This collapse happens so swiftly that the core becomes an object of extraordinary density. If nothing halts the contraction, the core transforms into a black hole, with a mass equivalent to that of the original star, but compressed into a far smaller volume. The outer layers may explode outward in a spectacular display, while the black hole remains behind as a silent remnant. Although it emits no light of its own, its presence reveals itself through its influence on the surrounding matter. As gas spirals toward a neutron star, it heats up, emitting radiation that can be detected from across the galaxy. These remnants reveal how the demise of a single massive star can give rise to one of the most extreme objects in the universe. The surfaces of neutron stars are made up of matter packed at astonishing densities. When certain stars explode, their cores collapse into compact spheres, primarily composed of neutrons, crammed together more tightly than any material found on Earth. Although the surface appears solid, the matter within is unlike anything you have ever experienced. At the very top layer, atoms are squeezed into a state where electrons combine with protons, resulting in a crust rich in neutrons. As you delve deeper, the density escalates to such extremes that the properties of matter become a topic of ongoing research. The gravity at the surface is so powerful that even the slightest irregularity could weigh countless tons. When these stars rotate or shift, stresses can accumulate in the crust until sudden adjustments release bursts of energy detectable as brief flashes of radiation. By studying these signals, scientists gain insights into the behavior of matter under conditions that are impossible to recreate on Earth. Neutron stars serve as a unique laboratory, allowing us to explore the fundamental nature of the universe. You are invited to continue this journey of discovery or take a moment to reflect on these incredible phenomena. Imagine a universe where exoplanets move through chaotic systems, their orbits constantly shifting under the influence of gravitational forces. In some star systems, planets travel so closely together that their interactions create a dance of gravitational pulls, never allowing them to settle into a stable rhythm. The orbits of these planets experience subtle tugs over time, gradually altering their shapes and tilts. In this dynamic environment, predictions become increasingly difficult, even for the most sophisticated models. Some planets may drift slowly inward or outward, while others might undergo cycles that reshape their orbits over long periods. The gravitational interactions can grow so intense that one planet could be flung into a new region of the system, or even ejected entirely. Observing these chaotic systems reveals the fascinating variety of planetary architectures across the galaxy. Not every system mirrors the orderly arrangement we see in our own solar neighborhood. Instead, many environments exhibit a constantly shifting ballet, where gravity orchestrates a dance that never fully repeats itself. As young stars form, they can send jets of material racing through the surrounding gas, carving out long channels. When a young star collects material from its surrounding disk, some of this gas is funneled by magnetic fields and expelled from the star's poles at incredible speeds. This interplay of forces showcases the extraordinary complexity of our universe, inviting you to reflect on the mysteries that lie beyond our own celestial home. Narrow streams of material flow outward in opposite directions, colliding with the surrounding cloud. When these jets strike, they compress and heat the gas, creating glowing regions that illuminate the path of the outflow. Over time, these jets displace large volumes of material, forming elongated cavities that extend far from the central star. The movement of the jets can change as the young star rotates or as conditions within the disk fluctuate, leading to knots and ripples along the channels. These formations provide scientists with insights into how young stars shed angular momentum and clear their birth environments. The jets showcase the immense power of early stellar growth and the intricate interactions between newborn stars and the clouds from which they originated. Meanwhile, ultra-faint dwarf galaxies, which contain few stars yet significant amounts of dark matter, present a different mystery. These tiny galaxies orbit larger systems and appear as faint smudges, requiring careful observation to detect. Although they host only a modest population of visible stars, their movements suggest a hidden mass far beyond what the stars alone can account for. This unseen mass is attributed to dark matter, which exerts gravitational influence without emitting light. The presence of dark matter enables these dwarf galaxies to maintain their structure, even in the absence of many visible components. As you explore the movements of stars in these faint systems, you uncover vital insights about the distribution and behavior of dark matter on small scales. These galaxies serve as time capsules, preserving ancient star populations that formed during the early stages of cosmic history. They offer you a rare glimpse into the conditions that existed long before the Milky Way took its current form. Their faintness and simplicity make them essential for understanding both dark matter and the early universe. You notice that star formation can come to a standstill when intense radiation evaporates the surrounding gas. In regions where massive stars ignite, their brilliant light fills the environment with heat. This radiation interacts with nearby clouds, causing molecules to break apart and drift away. As the gas heats and expands, it becomes too diffuse to collapse under its own gravity. Without this crucial collapse, the process of forming new stars slows down or may even cease altogether. This influence stretches across vast areas, shaping where future stars can emerge. Over time, the delicate balance between heating and cooling decides whether a cloud continues to develop dense regions or transitions into a largely inactive zone. Observations of these environments reveal intricate interactions between forming stars and the material surrounding them. Take a moment to reflect on these cosmic dynamics and consider how they impact the universe around you. If you're ready, you can continue exploring this fascinating subject, or simply take a moment to rest. You find yourself captivated by the delicate balance between radiation and gravity, a force that profoundly influences the rhythm of star formation across distant galaxies. Imagine planets where seas of liquid hydrocarbons replace the familiar oceans of water. On some icy worlds, far removed from their suns, temperatures drop so drastically that gases we know on Earth transform into flowing liquids. Methane and ethane, which drift unnoticed in our atmosphere, become dense enough to fill lakes and seas. These expansive bodies of liquid stretch across vast basins, shaped over millennia by rainfall composed not of water, but of hydrocarbon droplets. Picture a landscape where channels carved by rivers guide these liquids toward larger basins, creating coastlines sculpted by unusual weather patterns. In the sky, clouds of hydrocarbons gather, unleashing storms that replenish the lakes in a mesmerizing cycle. The chemistry in these alien environments is intricate and fascinating. Researchers believe that because carbon-based molecules react differently under such extreme cold, the interactions taking place at these low temperatures might yield compounds that are challenging to form in warmer settings. These otherworldly seas demonstrate that even in the faint light of distant stars, worlds can sustain vibrant climates, revealing that water, often considered essential for life, can take on many forms. You are left pondering the mysteries of the universe and the potential for life in the most unexpected places. Gamma-ray bursts unleash immense energy in an instant. These remarkable phenomena occur when certain stars reach their final evolutionary stages, collapsing into compact remnants, or when two dense stellar remnants merge. The resulting explosion emits a concentrated flash of high-energy radiation that radiates across the cosmos with incredible brightness. For a fleeting moment, this burst can outshine entire galaxies, even though its source may be no larger than a stellar core. The radiation travels outward in narrow beams. If one of these beams aligns with Earth, astronomers observe a brilliant flare that lasts from mere fractions of a second to several minutes. Following the initial explosion, an afterglow persists for days or even weeks as the expanding shockwave interacts with surrounding material. These bursts offer invaluable insights into the most extreme physical conditions known, including intense magnetic fields and rapid particle acceleration. By studying gamma-ray bursts, scientists deepen their understanding of how heavy elements spread throughout galaxies and how cataclysmic events shape the evolving universe. In fact, Some families of asteroids trace their origins back to ancient collisions, when rocky bodies traversed the early solar system on intersecting paths. Imagine a dramatic scene in the cosmos. Two large asteroids collide, their impact sending shards flying into new orbits. Over time, these fragments journey around the sun, spreading out into clusters that share similar characteristics and paths. By examining their colors, reflectivity, and movements, scientists can categorize these asteroids into families, unveiling the mysteries of their long-gone parent bodies. These families hold vital clues about the conditions that shaped the early solar system and the materials that were present during the formation of planets. As researchers delve into the study of these interconnected fragments, they can trace the timeline of ancient impacts and gain insights into how collisions influenced the distribution of materials that eventually formed moons, seas, and comets. Even now, these families are not static. They continue to evolve as gravitational interactions gently nudge their members onto new trajectories. In this vast expanse, planetary magnetic fields play a crucial role. They can capture charged particles, creating magnificent glowing belts. When a planet boasts a strong magnetic field, it extends into space, forming an invisible structure that guides these charged particles. Solar wind and cosmic rays often supply these particles, which become entrapped and spiral along the magnetic lines. As you contemplate this cosmic dance, consider how interconnected everything is. The remnants of ancient collisions continue to tell a story that spans eons. Would you like to explore more about these celestial wonders, or perhaps take a moment to reflect on their significance? Imagine a world where particles collide with atmospheric molecules, creating a soft glow that encircles the planet in vast luminous belts. And these belts, dynamic and ever-changing, brighten and shift in response to bursts of stellar activity as waves of charged particles flow into the system. The behavior of these trapped particles offers a glimpse into the strength and shape of the magnetic field, revealing secrets about how magnetic shielding can affect a planet's ability to support life. Strong magnetic fields act as protective barriers against harsh radiation, showcasing the intricate dance of magnetic forces that shape the structures surrounding planets and influence their long-term evolution. Now, consider the profound effects of gravity near black holes. As an object approaches the intense gravitational pull of a black hole, time itself begins to behave differently. The fabric of space-time stretches, altering how time flows for both the object and distant observers. To those far away, it appears as if the object slows down, almost frozen at the boundary where escape becomes impossible. Yet, for the object itself, time continues to march on. This fascinating interplay illustrates how gravity not only influences the paths of objects in space, but also alters the very rate at which time progresses. As you reflect on these cosmic phenomena, consider how they intertwine to shape our understanding of the universe, inviting curiosity and wonder about the mysteries that lie beyond. As you approach a black hole, you notice that the distortions around you intensify. Instruments designed to capture signals from matter spiraling inward reveal fascinating shifts, confirming that time itself slows down in such extreme environments. Grasping these effects is crucial for understanding how black holes interact with their surroundings and how gravity governs the universe at its most intense. You begin to realize that time is not a constant backdrop. It is a fluid entity shaped by mass and motion. In certain galaxies, you find that they rotate around invisible clusters of dark matter. While these galaxies are filled with stars, gas, and dust, their visible components alone cannot explain the astonishing speeds at which they spin. Instead, an unseen mass exerts a gravitational force, binding the galaxy together despite its swift movement. This hidden mass creates a halo that envelops the visible disk, extending far beyond its outer edges. The stars within this halo follow orbits determined not just by the visible matter, but primarily by the distribution of dark matter. As you observe the rotation curves, you discover that the